Hello, everyone. Welcome back. So today's lecture is actually going to be a repetition of last lecture with several corrections and improvements. And this one will be recorded. So let me start over for the purpose of recording. Hello, everyone. Welcome to CS 700 Computer Science of Continuous Data Algorithmic Foundations of Numerics. And today we're going to talk about computational complexity on generic metric spaces. And the crucial part here is, of course, to find the right notions. And the notions are to be designed in such a way that they, on the one hand, generalize, extend, and include the notions from the real case where we already have found the right notions, the right definitions, and the right properties on the one hand, generalizing the real case, and on the other hand, also generalizing computability on general spaces, namely on topological spaces and metric spaces or a special kind of topological spaces. And we're kind of aiming for the synthesis of both generalizing real complexity as well as quantitatively refining generic computability. And that will be our computational complexity theory for metric spaces. Okay, let me show you the slides here. Here we are. And this is going to be the content of today's lecture, Complexity and Metric Spaces, Chapter 6. First, we talk about the complexity of single elements, single points of a certain fixed metric space equipped with representation as formalizing an encoding of that space over one of our basic spaces, usually Cantor space, but also pair space. Then we're going to step up from single points to transformations between points, that is, to functions, and of course, focus on continuous function, because every computable function, as we already know, must be computable, must be continuous. And then we ask, what about the relation between complexity and quantitative continuity? We know that there is such a relation in the real case, and we hope and we want this relation to carry over in a certain sense to the generic metric case. And this will be our guidance when developing the right notions. And this one such right notion will turn out to be polynomial admissibility. That is, a polynomial quantitative refinement of qualitative admissibility according to Kreitz and Weyrauch, which we know is the crucial condition for computability investigations of encodings. And based on that notion, then we can actually state a polynomial version of the Kreitz-Weyrauch Main Theorem correspondence between quantitative continuity of functions and quantitative continuity of realizers of that function. And that all will turn out to depend on intrinsic metric properties of the space under consideration, namely entropy, which is defined by Kolmogorov as a quantitative capturing qualitative compactness, which we'll review in this slide, and then we'll proceed to construct the standard representation canonical way of encoding compact metric spaces that which is closely related actually to the entropy. And then we'll see that for large spaces, for spaces with large entropy, and particularly for function spaces, we need to step up also about the basic spaces and proceed from Cantor space to a certain larger space, a space with exponential entropy. And that will be our last slide of today's lecture. So let's begin with talking about computational complexity of elements of points of a metric space. And it may help to keep in mind the following kind of dictionary that translates between qualitative notions on the left and quantitative versions on the right, which we're about to develop. And the goal should be such that qualitative computability becomes refined to quantitative computational complexity, qualitative topology, like continuity, notions of qualitative topology will become quantitative versions in the metric setting, such as quantitative continuity captured by a modulus. And indeed, uniform continuity will become modulus of continuity. Compactness, as I said, qualitative notion will become entropy, quantitative notion. Standard important fact is that the continuous image of any compact space is again compact. And on the quantitative version of that, this is some very nice lemma of Florian Steinberg, which relates quantitative compactness, namely entropy, and quantitative continuity, namely modulus, to the entropy of the image space. And as basic spaces in computable analysis, one usually considers Cantor space or Beer space, or more general so-called equilogical spaces, as developed by Dana Scott and Andre Bauer and co-authors. And we argue that the corresponding category for basic spaces or for complexity investigations are actually compact ultrametric spaces. And the prime example there are Cantor space, Beer space, and the second order spaces that we are going to investigate and consider in the last slide. So let's get started with notions and properties of computational complexity of points from a generic metric space. And this generic metric space will be equipped with a representation over, let's say, Cantor space of infinite binary sequence, equipped with this ultrametric 2 to the minus the first index where the two infinite sequences differ. And recall what we defined to compute an element of Cantor space in time t means that the nth output, the nth entry in this infinite binary sequence must appear in the output within at most t of n steps. More precisely, all entries in this infinite binary sequence up to and including the nth entry should appear within t of n steps. And right, that's one intuition to look at this notion means that this finite initial sequence is kind of an approximation to the final infinite sequence, capital U. Finite approximation, this is a finite initial segment, and it approximates U up to error 2 to the minus n in the sense that all other extensions of that finite initial segment all differ from U up to error 2 to the minus n. That's according to the definition of the metric. That's what the metric means. It means all extensions coincide up to and including the nth entry. So the first discrepancy can occur only at the n plus first place. And similarly, for computational complexity on our other popular basic space, namely Beer space. And we also have, and like to recall, a similar notion for computational complexity of single real numbers. Namely, that means to approximate the real number up to array 2 to the minus n within t of n steps, and approximating array 2 to minus n means outputting the first up to the nth numerator of the diintegration approximation. So again, this is a finite initial segment of the infinite sequence of approximations with the property that any extension of that finite segment to an infinite sequence, to an infinite name of some possibly other real number, have a distance at most 2 to the minus n. Um, so yeah, in this sense, this is an approximation up to array 2 to the minus n. And I keep emphasizing that because this approximation perspective will be the key for us that leads to the generalization to other metric spaces. And let me also remind you what a representation is. Representation is a surjective representation of a space X is a surjective partial mapping onto the space X, whose domain is some arbitrary subset either of Cantor space or of Baire space. And the psi name of X is any infinite binary or integer sequence which gets mapped by this representation to X. And yeah, I'll return to that in a minute. And the representation that connects this abstract setting with the real setting that we discussed here is the representation which we called delta. Delta is the one that takes an element of Baire space, an infinite sequence of integer as numerators to dyadic approximations, and maps that to the real number which gets approximated in this sense, provided that such a real number exists. If it exists, then it is unique. So, but in general, it may not exist if the sequence is strange, and therefore this is a partial mapping. And so we can now rephrase that ad hoc notion of computational complexity of a single real number as computational complexity of basic space, here let's say Baire space or Cantor space, when equipped with that particular representation. That will be our guide. That's what we want to generalize to other spaces. So in both cases, it's about outputting a finite prefix of a name, where a name is now an infinite object. Here over Cantor Baire space, the canonical representation is of course just the identity, right? So representing Cantor space over Cantor space, that's what the identity does. Representing Baire space over Baire space, this is what the identity does. And in this sense, this is also a finite prefix of a name of Cantor space, a point, namely this infinite sequence. And now we're ready to define. Remember that definitions are the crucial part in our frontier area of research of continuous complexity theory. So let's fix the representation of a metric space X with metric D and define what it means to be compute a point, an element of that space in time t. Namely, it means to output again a finite prefix of a name of X within t of n steps, the same story as in the previous cases, such that, well, it must be a finite prefix of a name. That means there must be an extension of that finite segment sequence to an infinite sequence, which is a name of X, right? So this is the first condition. And for convenience and abbreviation, let me abbreviate that extended that infinite name with v. No, that should be u anyway. And now we can maybe state the second condition. Maybe the second condition says that all these extensions, all these possible extensions of this finite prefix must have distance to the actual element. It should be a x at most t to the minus n. And the important difference to two ad hoc notions above us. In the both ad hoc notions, we count the number of steps independent of n, such that the approximation is up to error 2 to the minus n. But the finite prefix here also has length n, and that's kind of a degenerate case, because later we'll see that both these spaces have linear entropy, but in general we're going to admit or consider finite prefixes of arbitrary length, provided that these two conditions hold, namely this arbitrary length must be feasible to output within t of n steps. So that in particular means mu must be less or equal to t of n, because in t of n steps we can only output n elements for sure. And the second condition is that all extensions of this first mu elements, they must be approximation. They must have distance to it, to the actual element 2 to the minus n. And in general, this, depending on the space, this may require mu which can be larger or smaller than n actually. Only in these two cases we can actually fix mu to be equal to n. And yeah, what's the relation between mu and n anyway? To this end, let us recall the notion of a modulus of continuity. A modulus of continuity, as we recall, is an integer mapping such that whenever the arguments differ by no more than 2 to the minus mu of n, then also the values differ by no more than 2 to the minus n, where arguments and value are, of course, measured in terms of different, possibly different metrics. And this condition here now is exactly the condition of a modulus of continuity, right? Namely, whenever the initial segments, finite prefixes, agree up to the mu's position, that's exactly what means, according to the metric here, that the distance is at most 2 to the minus mu of n. And the requirement 2 now says that if this agree up to 2 to the minus mu of n, then the values under the representation must have distance at most 2 to the minus n, so that this is actually a condition for that mu must be a modulus of continuity of the representation now considered as a mapping from Cantor or Baire space onto the space X. So here we see this in this notion implicitly reoccurring this notion of a modulus of continuity, but the subtle point here, now we only require this to be a pointwise modulus of continuity for different points. The mu could be different and could depend differently on the approximation error 2 to the minus n. Okay, so this is our definition for computational complexity of a generic metric space, a point in a generic metric space equipped with a generic representation. And let us verify that this indeed generalizes and includes the above two particular cases, namely, yes, indeed. So when we talk about Cantor space equipped with the identity, then for mu being equal to n, the identity, we recover exactly this definition, observing that all extensions by very definition satisfy this condition. And the same for the real case, namely, yeah, in the real case, we again can choose mu being equal to n and arrive at this very condition. So this is the point is, the message is, this is indeed a generalization of the first two cases to an arbitrary generic metric space equipped with an arbitrary generic representation. So it seems to be a good definition. And now we step up from computational complexity of a single point to computational complexity of a transformation between points, from points to points of possibly different metric spaces, namely computational complexity of function. That's going to be, that's what we want to define. And again, our guidance will be the ad hoc computational complexity notion that we already have for Cantor space with the identity as representation, for Baire space, again with the identity as representation, and for real functions. So let us recall these two notions. The notion of computational complexity for partial function from and to Cantor space. Time t means, again, to output the image f of u, which we call v, in time t, in the very sense of computing a single point, computing the single point v as an infinite binary sequence of Cantor space. And the subtle point is what this may not depend on, right? So, of course, v will depend on u, right? So it depends on the argument, but the definition says that the time to compute v must not depend on u. So here the time, remember, means number of steps it takes to output up to the nth element of v, regardless of u. That's was a subtle but important point that we have kept emphasizing when we investigated computational complexity on Cantor space, and that I need to emphasize again here. And similarly, our notion, a talk notion of computational complexity of a real function would consider also input of a sequence of approximations to the argument and output of a sequence of approximations to the value. And computational complexity means that outputting the error to the minus n approximation to the value must occur in time t. So that's exactly our definition of computing the single real number in time t, but with time t now again independent of the argument. So the actual real number will depend on the argument x, but the time it takes to produce that must not depend on the argument. So right. It must not depend on the argument, nor must it depend on how the argument is approximated. It must not depend on the sequence of numerators am. As you recall, every single real number has uncountably many such sequence of approximation, and the computation may depend and will depend on that, but the complexity, the cost of the computation, the number of steps must not. And you see here a common story, namely we define computational function by computation of single elements, named the value, and the computational complexity must be independent of the argument. Yeah, because it's the definition of computational complexity of single points that we combine here with computation depending on the argument, but the computational cost being independent of the argument. And now we take these two ad hoc notions and generalize them to devise the notion of computational complexity for function between spaces equipped with the representation space x equipped with respect representation xi, space y equipped with representation epsilon. And again, this notion will be in the similar story, namely we define to compute the value of that function as a single point to be computable in time t, in this very sense that we defined here, computation of a single point in time t with respect to the representation. And following the same theme as here, the computation may depend on the argument. The computation may depend on how the argument is encoded, which name, but the computational cost must be independent of that, must be kind of the worst case cost. So here we see our definition. We fix two representations of metric spaces X with metric D and metric space Y with metric E. And we recall what the realizer is of this function with respect to this representation. And basically, it's something that makes this diagram commute. So first follow xi, then follow f must be the same as when we first follow the realizer and then follow the representation epsilon. Starting point is here we can actually allow for an extension. We don't prescribe the behavior of this path on arguments that are outside of the domain of this composition. So recall this is reflected by this symbol. It means that the right-hand side can be an extension of the left-hand side, or that the left-hand side be a restriction of the right-hand side. And now we define computability in time t of a function with respect to these two representations, namely that on input of any xi name of an argument in the domain, the computation must produce a epsilon name of the value y equals f of x in time t. And so again, the theme is the same as above. The time t is by definition the very time it takes to compute a single point in this sense with these two conditions. But the computational time must be independent of the argument x and independent of the xi name of x, whereas the computation itself will of course depend in general on both. So that's again important to observe here, following all these discussions and motivating examples here. And you see by our very design of this definition, it generalizes the above two ad hoc cases. So it seems like a good definition. And again, observe that now here the modulus of continuity arises here. And now it's not just pointwise anymore, it's a uniform modulus of continuity. And I'd like to, I need to emphasize two things. First, that this notion of computing a function between represented spaces in time t is usually, not always, but usually very different from what it means to compute a realizer in time t. Because when computing a realizer, our definition says how long does it take to output the nth symbol of the realizer's value, where here it means the time it takes to output the mu's element, right? And as you recall, mu is equal to n in these two examples cases, Cantor and real, but in general, depending on the space, mu can be very different from n. So don't confuse computing a xi epsilon realizer of f in time t with computing with xi epsilon computing the function f in time t. These are two different notions in general. Only for at least for these two cases they coincide, but in general they don't. That was my first important remark. And my second important remark is what about our main theorem? So we wanted, we have the main theorem that says computable functions have continuous functions have continuous realizers and vice versa. And we wonder whether quantitatively continuous functions have quantitatively continuous realizers as this notion of complexity. And obviously, the answer again is negative in general, because already for computability, for this correspondence, qualitative correspondence, we had to impose this additional new condition that the representations under consideration are admissible. So we already expect some similar condition to be necessary for the representations, some refined condition in order to arrive at a quantitative correspondence between quantitative continuity of a function and quantitative continuity of a realizer. And again, what we expect will be guided or obtain guidance from considering our prime example, namely the Cantor space and the real case functions. So for Cantor space, we had this correspondence, as you recall, namely, that computation in time t, so computational complexity, gives rise to and suggests quantitative continuity, a modulus of continuity. Actually, um, direct correspondence time t means t is a modulus of continuity, and this is tight, obviously. For the real case, the correspondence between computational cost and quantitative continuity is a little bit less tight, is a little bit more relaxed. Namely, if a function, a real function is computable in time t, then it has a modulus of continuity O of t of O of n. And less tight here means relaxation or a slack in two positions, namely first, instead of n, we have O of n, so we have here some possible constant factor and some possible constant overhead, and maybe even other lower terms here in the argument, and the same in the value, in the return value of the time bound of the integer function t. So here it's big O and here it's big O. So it's not exactly tight here. And also notice that I haven't proven that yet. We're going to get to proof later. But this is true, and this will provide our guidance to then one kind of source of guidance for generalizing this notion, for generalizing our conditions on the representations under consideration. Namely, the real case is implicitly always equipped with this representation delta, the dyadic representation. And regarding the connection between quantitative continuity, so this is connection between complexity and quantitative continuity. This is connection between quantitative continuity of the function and quantitative continuity of the realizer, namely for any non-decreasing integer mapping mu, these two are related, provided that we allow for some polynomial slack in the argument and polynomial slack in the value. So this is again less tight, actually. Previously, we had here big O of n in the argument and big O in the value, and here we have polynomial in the argument and polynomial in the value. And if we permit that in both cases, then we get this equivalence. So there's possible loss moving from here to here and back. Then there may be some loss, there may be a larger polynomial, larger degree, larger coefficients, and same for here. Okay, so this will be our guidance when we now construct the conditions for which representations we want to consider for real complexity, for complexity theory of functions between compact metric space. As you recall, or this definition here does not yield in general such a connection between quantitative continuity of the function and quantitative continuity of the realizer, because it did not impose anything at all on the representations. So the least we want for the representations for them to be qualitatively admissible, which, as you recall, means that the representation must be continuous as a partial mapping from Cantor space onto this metric space X, and it must be kind of maximal with respect to this notion of continuous reduction, namely among all other possible surjective such partial mappings onto X. Let's call such a fix and call such a mapping xi prime. This must admit a continuous reduction to our original representation. So it means our original representation must be maximal with respect to this partial order. And let's recall that this maximality is very similar to the notion of NP completeness, which also is actually a maximality condition with respect to partial order. Only there, the first condition, continuity here, is replaced by that the decision problem must be in NP. And the second condition, namely universal reducibility. Here, every continuous surjective function must be continuously reducible to this. And in the NP case, discrete decision problems, every other NP problem must be polynomial time reducible to this decision problem. We'll also need to recall the notion of a standard representation. A standard representation is a particular kind of admissible representation, namely one where this continuous reduction holds not just for all surjective partial mappings from one of the basic spaces to X, but holds for actually all partial mappings from one of the basic spaces, not necessarily onto, but to X. So standard representation satisfies this strong property. Admissible representation satisfies this for all surjective such mappings, and standard representation satisfies this for all such mappings. And an important part was to show that standard representation actually exists. Otherwise, it would be a theorem about the empty set. And so let me remind you what continuous reduction means. It means having a continuous psi prime comma psi realizer of the identity, because they're both representation of the same space X. So identity from X to X, or boiled down more explicitly, there must be some continuous function from the domain of the first to the domain of the second, such that when first executing this translation, this continuous translation, and then psi, then one arrives at the same as if we apply the other representation psi prime to begin with. And now let's take that well-established qualitative notion of admissibility, qualitative condition for representation, and turn that into a quantitative condition such that we recover the real main theorem. So we know the real main theorem, and we want to recover and obtain a general main theorem that should include the real version, like this with this slack. If we replace our condition of admissibility with a yet to be designed notion of quantitative admissibility. And of course, we want this our original representation delta for the real case to be admissible, and maybe actually even to be a standard representation. And this is actually going to be true. So let us recall the main theorem that justifies and explains us considering admissible and standard representation. So the main theorem has two parts. The first part says if we have a standard representation, then continuous functions have continuous realized and vice versa with respect to that standard representation. So here on this qualitative level, we have a correspondence between continuous functions and continuous realizers. And this statement that this is not a theorem about the empty set, namely that every second countability zero space has a standard representation. So it's actually a non-trivial theorem based on this second claim of the Kreitz-Weierach main theorem. And yes, as I kept emphasizing, Matthias Schröder has generalized this hypothesis considerably, but this is unfortunately not the focus of our current chapter, because we're interested in heading towards computational complexity, as you recall. So for standard, and if we know this for standard representation, then it immediately also applies to admissible representation. And let's now look at how we refine that quantitatively, and our guidance, our quantitative properties of the dyadic representation for the real unit interval, which we already know to be a good representation. So we're going to look at its properties, and one property of this representation is that it has a polynomial modulus of continuity when considered as a mapping from Cantor space onto the real unit interval. It's a partial mapping, but yeah, it has a polynomial modulus. And now we're going to define uh, right, a quantitative version of, so this is going to be a quantitative version of the first part, right? So first condition of admissibility or standard representation says that it must be continuous, and we want this, we will want polynomial reasonable representation to be have a polynomial modulus of continuity. That seems like a great notion. Let me say that again. Admissibility and standard representations are required to be continuous, a qualitative property, and it seems like a great natural idea to require a polynomially admissible representation to have a polynomial modulus of continuity as a quantitative strength of this qualitative uh, continuity, and it's a great choice because, as I said, the real representation delta satisfies this condition, so we're actually going to have that covered. And our general second condition of admissibility similarly gets strengthened quantitatively, maybe by refining continuous reduction, like in this sense, to optimal reduction in a quantitative sense. So here's our definition of polynomially optimal reduction, which will strengthen or continuous reduction in the sense that now the reduction function must have a modulus of continuity, which is called mu here, that satisfies the following condition. Well, let's have a look again at this condition, right? So it means that the reduction, when followed in execution composed with a representation psi, should be an extension, not necessarily proper, but an extension of the representation psi prime. And now let's look at the modulus of continuity of this here. So if f has modulus nu, and if psi has modulus mu, then, as you recall, the composition of the two has the composition of the moduli as nu modulus, but the composition now with order reversed, right? So here first comes f, then comes psi. Here first comes f, then comes g, but the modulus is first comes the modulus of g, and then comes the modulus of f. And similarly here, the right-hand side therefore has a modulus, first the modulus mu of psi, and then the modulus nu of f. So, and this will of course be a modulus of the left-hand side, because the left-hand side is a restriction of the right-hand side. So any modulus of continuity of the right-hand side will always be a modulus of continuity of the left-hand side. So if we denote the modulus of continuity of the left-hand side by a mu prime, then that mu prime will be at most as large as the modulus of continuity of the right-hand side, which we just calculated to be nu after mu. And our condition, so that holds automatically. But our condition is that the actual modulus of the right-hand side should not be too much larger. So it must be at least as large, but not too much large. And that's the condition we want to oppose, namely the modulus of continuity of the right-hand side, which is this composition, right? First mu followed by nu, right? First mu modulus of this followed by nu modulus of this should not be too much larger than the modulus of the left-hand side, namely should be at most modulus of the left-hand side pre-composed with some polynomial slack. Okay, we already had this polynomial slack here as a way of relaxing both to be equal. But the important thing here is after mu prime, there's no slack allowed. Here we have slack in the argument and slack in the value. Here we have slack only in the argument. And the reason for this requirement is because then that makes actually the relation between these representations transitive, right? Remember, polynomial reduction turned out to be transitive, and here we're polynomial reduction between decision problems. Here we talk about polynomial reduction between the representation, and again our notion of this reduction better be transitive to be a reasonable notion, and this is achieved exactly by allowing here a polynomial select, but not here, nothing here. Okay, so to summarize, this is a good notion in that it is transitive. And also let me point out that here the quantifiers over the various moduli, right? So here we have a reduction, continuous reduction with a modulus called nu, strengthening quantitative continuity. And we have moduli of psi and psi prime. And the requirement is that this holds for some modulus mu of psi. Of course, mu is here on the left-hand side, must be less or equal. There's no point in requiring it for every modulus mu. Of course, then the inequality would be triply wrong. Whereas for the right-hand side, we actually require that for every possible modulus mu prime of psi prime. And as you recall, to every modulus on of a function on a compact domain, there's always a minimal modulus, which is still a modulus. If we take larger, the set of all moduli is a cone, but we're interested in kind of small in the minimal moduli. And so we can now replace in this definition the quantification over all moduli by using specific minimal moduli, and that's going to be equivalent, obviously. Okay, so right, that's now our definition of polynomial reduction, quantity, not polynomial time, but polynomial reduction because of this polynomial slack here. And it's transitive, so it's a good notion. And now we impose that as quantitative strengthening of condition D2 from admissible to polynomial admissible representation. And the first good news is that this new quantitative version of reduction is actually satisfied by our real representation delta. And one can prove, although I won't do that here right now, that any other representation psi prime of the real unit interval admits a polynomial reduction to the dyadic representation delta. And one thing that deserves being elaborated is that in the original definition, we require such a reduction only for every continuous surjective or admissible, or for every mapping continuous mapping psi prime in the case of standard. But the point is only for continuous we require that. Here we say that holds, the claim says that this holds for every possible psi prime, whether it is surjective or not, and even whether it's continuous or not. And this is kind of surprising, but as you can see here, if this is not continuous, or if it's just pointwise continuous and not uniformly continuous, then this simply does not have a modulus, neither minimal one nor any other. So in this case, the statement boils down to the empty condition, which is of course always satisfied. So this is indeed a generalization or strengthening of that condition. Although it seems we drop a hypothesis, it still includes and implies continuous reduction whenever the left-hand side is continuous. Okay. And now we can, with this guidance from the real case, we can state and define our notion of polynomial reduction between the and polynomial admissibility. So here we have polynomial reduction, and we say that a representation of a metric space X is polynomially admissible or polynomially standard. Here we are. If, okay, let's strengthen the first condition from qualitative continuity to quantitative continuity, having a polynomial modulus of continuity. But this is not going to be our definition. Instead, we're saying has a modulus of continuity which is polynomial in eta, where eta is going to be the entropy. So the naive idea is to require that the modulus be bounded above from the entropy, and we're going to explain in a minute why. Well, the very first naive condition is that the modulus of continuity should be polynomially bounded. And that's a bad idea, as we're going to explain in a minute. And the next best idea is to require that the modulus is bounded polynomially in the entropy. And that's exactly what we do here with polynomial bounded into entropy again, allowing for this polynomial slack in the argument and in the value. And the second condition becomes this polynomial reducibility. Any other representation, continuous or not, or any other function, partial function, not even necessarily onto X, must admit a polynomial reduction to this representation in this very sense. Okay, that's now finally our definition for polynomial admissibility. And for polynomial standard representation, we require that not just for surjective such mappings, but for all. So same storyline as previously in the qualitative case. Now, is that a good definition? What would we expect from that definition to convince us that it's a good definition? Right, I first need to mention that eta here denotes the entropy of the space under consideration, but I will say more about the entropy on the next slide. So please stay tuned for now. Just observe that entropy is kind of very much like modulus, just a function total mapping from natural numbers to natural numbers. Okay, and based on this definition now we can restate and rephrase concisely our observations or lemma about properties of the dyadic representation, namely the dyadic representation is indeed polynomial standard representation. It satisfies all these properties without even requiring to be surjective. Again, I'm not going to prove that right now here. Maybe that's going to be part of the final exam, who knows? But the point is, this justifies this our definition because the definition applies to a representation for the reals, which we already know to be a good representation. And indeed, now we can call it polynomial standard representation and speak about it. Okay, and that's our first argument of convincing you that this is a good definition. Our second is that indeed now we have a polynomial, a quantitative version of the qualitative Kreuzweil Main Theorem. And to this end, recall that one important claim of the Kreuzweil quantitative Main Theorem was that every second countable T0 space has a standard representation. And similarly, we can show, and we will do that on the next slide, that every compact metric space whose entropy is at least some bounded from below by some power law, n to the epsilon for any positive epsilon, could be like n to the 0.0001. But as long as it is bounded from below like that, then the space has a polynomial standard representation. So that's good news. We're not talking about the empty set of polynomial standard representation, at least for this large class of spaces. And observe that example ever connected metric space has actually at least linear entropy, as Duncan Lim proved. Okay, so that's first main theorem, and as I said, let's wait for the proof until the next slide. But for now, let us also state the other two items of a main theorem, polynomial main theorem, and recall that the qualitative main theorem would relate continuity of a function with continuity of a realizer, both way an equivalence. And similarly here, we have two implications actually. A certain modulus of continuity for the function implies a certain modulus of continuity of the realizer, and vice versa. Certain modulus of continuity for the realizer implies a certain modulus of continuity of the function, which is kind of great and what we want and what we can expect. So if f is item b, if f has a modulus of continuity mu f, Then it also has a realizer with respect to these representations, which is continuous. We already know that from the main qualitative main theorem, but actually realizer which has again a modulus of continuity that satisfies there's an inequality and bounds in this new modulus, which will let us abbreviate with mu f, satisfies this bound. Let's look more closely at this bound. So here on the left-hand side, we see that modulus mu f. So it's an upper bound on the modulus of continuity of the realizer. It cannot be too large. It cannot be too bad, quantitatively continuous, but followed by some new quantity that was not present and maybe surprising, namely the entropy of the codomain. Right? So this is the entropy of the codomain, and this composition is bounded. Okay, not just the modulus of continuity of f, but the composition of the two quantities is bounded by, what do we have here? Modulus of continuity of the function, unrepresented function. Naturally, that will occur with polynomial slack in the argument and polynomial slack in the value, right? And followed by the entropy of the domain x. Okay, and that's the first statement. Again, I'm going to prove that in a few minutes. But for now, let's just look and understand the statement. That's half of the statement. Continuity of the function implies continuity of the realizer quantitatively in this sense. And the converse is also true if the function has a continuous realizer with a certain modulus, mu capital F, then the original function is also continuous and has a certain realizer, has a certain modulus mu f. Namely, again, we have this upper bound. It cannot be too large. But now the modulus of continuity is composed afterwards with the entropy. Here it's pre-composed with the entropy of the codomain. Here it's post-composed with the entropy of the domain. That's the difference here. And also on the right-hand side of this bound, upper bound, here we have polynomial slack, modulus of continuity, polynomial slack entropy. Here we have polynomial slack entropy of the codomain, here of the domain, followed by polynomial slack, followed by modulus of continuity of the realizer. So we have, indeed, this is a quantitative strength of the main theorem. Main theorem says continuous function, continuous realizer. Here we says uniformly continuous function with modulus, realizer with modulus, and converse, realizer with modulus implies function has some modulus. But also let me point out that on this slack, all these kind of losses in tightness that is here hidden under these polynomials do not cancel out if we go back and forth between this. So if we start with a certain function with a certain modulus of continuity, right at an upper bound on the modulus of continuity of the realizer, then apply this part of the theorem with this upper bound and the modulus of continuity of the realizer, and return and recover an upper bound on the modulus of continuity of the function. This will in general be larger and possibly much larger than the modulus we started with because of all these polynomial slacks. And an important part of research is to find spaces for which this polynomial slack can actually be improved and tightened to linear slack. Okay, but that's not the topic of our lecture because this is actually current ongoing research. Okay, so that's now a polynomial main theorem that applies to compact metric spaces with certain lower bounded entropies and to representations which satisfy this quantitative version of admissibility, polynomial admissibility. And what I do owe you is a proof of this theorem. Okay, and that's what we're going to do right now. So let's see, let's first prove item C, but before doing that, I need to state the already promised correspondence, quantitative correspondence to the qualitative fact that the continuous image of a compact space is compact. And here's the version that says if the image is not just continuous, but quantitatively continuous with modulus mu, and if the domain is not just compact, but has a certain entropy as a quantitative version of compactness, then the range is indeed not just compact, but again has a certain upper bound on the entropy. So you see how this is a quantitative strength of the qualitative property that continuous images of compact sets are compact. And this is easy to prove once you know the statement. I think, as in many cases, knowing the statement is halfway to the proof, and here it's maybe even 3/4 of this proof and the statement, and its proof was pointed out to me by Florian Steinberg. So credit who is credit to. And now let's apply this to representation, right? So representation here is surjective, right? So that's part of the being a representation. So the entropy of the domain is this. The modulus of what is the entropy of the domain? The entropy of Cantor space, we will see in a minute, is linear. So we can drop that actually, right? It doesn't change much to recompose with the identity function. And here's the models of continuity of the representation. And that composition will be at least, right, as large as the entropy of the range. And what is the range? The range is X. Of course, we're talking about a representation which is surjective and therefore has range X. So we immediately see that the entropy of X can be at most the modulus of continuity of Xi, which follows from here. Left-hand side is the entropy of X. The entropy of Cantor space is the identity, and this is just a modulus of continuity of Xi. Okay, that's an important upper bound on the entropy, or put differently, it's a lower bound on the modulus of continuity, and this is necessary. So now we can understand maybe the first condition better of polynomial admissibility, which says basically that this right-hand side cannot be too much larger than the left-hand side. It must be larger, right, according to Florian Steinberg's lemma, but it's required, polynomial, at least for polynomial admissible representation, to not be too much larger. Namely here, the right-hand side is the left-hand side of the inequality, and the left-hand side here is the right-hand side, but again with these two polynomial legs here and here. Okay, so you know that this is necessary. Now we can actually proceed to the proof of item B and item C, and let's look at item C first. What does item C say? Right, so as you recall, here this is our definition of a realizer, that if we first compose these two, that should be a restriction of if we compose these two. Now, hypothesis in item C says that this one has modulus mu f and is followed by modulus of continuity of upsilon. Modulus of continuity of upsilon is at least is the entropy of the codomain entropy of epsilon of y, and this is exactly what you see here. So the modulus of these two moduli composed are at most the modulus of f mu f composed with a modulus of this, and by this very condition here, apply this to the representation upsilon. This means the modulus of continuity of upsilon is bounded polynomially in the entropy of the codomain y, so that this gives exactly the right-hand side. The right-hand side is an upper bound on the modulus of continuity of this composition here, of this composition. And since this here is a restriction of that, this modulus will also be a modulus of this, right? And so that this modulus will be at most as large as this right-hand side. So what is the modulus of this this side of this path here? It's the modulus of f first, followed by modulus of psi. So that's basically this, except for the modulus of psi is upper bounded by the entropy of x. So using these two conditions here, one recovers and can immediately obtains this condition. And for this condition, we apply the second part of polynomial admissibility, the one with number Roman 2. Maybe we apply this. Let's apply this to the representation upsilon, not to psi, but to upsilon. And let's consider an alternative mapping upsilon prime, which is the composition of these two, right? So these two, this is maybe not a representation, it's not surjective, but it's a mapping from Cantor space here. And let's compare this to this representation. And since this representation is maximal, it means that it must be a polynomial reduction from this function to this function, and polynomial reduction means exactly this. What is here the right hand side, namely the modulus of f followed by the modulus of psi, and the modulus of psi we already know to satisfy this condition. And this will be also modulus of continuity for this composition, and this is exactly what is stated here using the second hypothesis. So now this hypothesis here, in order to prove item B, we apply this here to the modulus of continuity of upsilon, which is upper bounded by the low bounded by the entropy of y, and here we have the modulus of continuity of the realizer. So this establishes item B and C of our main theorem, and it remains for us to prove item A, namely that every compact metric space with at least that entropy has a polynomial standard representation, and I need to remind you what is actually entropy. So let's do that, and this is this slide. So what is entropy? Entropy has been defined by Andrei Kolmogorov in 1959 as a quantitative version of compactness, namely the entropy is like the modulus of continuity function from natural numbers to natural numbers, which captures or counts how many balls of radius 2 to the minus n are sufficient and necessarily to cover the space. And as you can recall, every compact metric space can be covered by finitely many balls of a certain radius. And how many, this is exactly what the entropy captures. And as usual, like with modulus of continuity, we consider powers of 2 for here. And this is an optimality condition, right? So every larger modulus of continuity is again a modulus of continuity, but for entropy, we only consider optimal, that is minimal entropy, so that smaller is not an entropy anymore. Okay, so every compact metric space has an entropy, and some spaces have large and some have small entropy. Let's look at some examples. So for example, here you see the d-dimensional cube, hypercube in dimension d, and when k is equal to 0, that's actually the unit cube, and when k grows, it's a larger cube, as you can imagine. And the statement says that the entropy is basically up to some constant or actually additive term, the dimension times the sum of the parameter measuring the balls and k. So that when you consider the unit cube, it means that the entropy is d times n asymptotically. And when we consider it in dimension 1, and d is 1, then the entropy is actually n that is linear with constant coefficient. Okay, that's our first family of examples. And our second example is actually Cantor space, which has the identity as entropy. And right, but before that, let's now have a look again at the statement about the modulus of continuity of delta, right? So I've said that the dyadic rational representation is polynomially admissible, but polynomial admissibility had this hypothesis, right? So what is the entropy of the real unit interval? As I said, it's linear, so that we have here polynomial, linear, polynomial, that is again a polynomial. So indeed, the dyadic representation satisfies the first condition of polynomial admissibility because the real unit interval has linear entropy. Okay. And how about the Cantor space? Cantor space has actually also linear entropy, has the identity as entropy. And I won't prove that here. And but finally, let's look at function spaces. And this is Euclidean space, this is Cantor space, and this is a certain function space, namely the space of one Lipschitz function, total function from X to Cantor space. So this is a space of, this is actually a compact space when equipped with the supremum norm on these functions, right? These are total one Lipschitz, that is non-expansive functions from X to Cantor space. And by Arzela-Ascoli, these are equicontinuous, namely they are one Lipschitz, and they are pointwise bounded because Cantor space is compact. And thus by Arzela-Ascoli, the set of these functions is compact again, compact metric space when equipped with the supremum norm. So we know it has an entropy. And which entropy? Well, the entropy depends on the geometry of the domain X a little bit, but mostly depends on only on the entropy of the domain, namely the entropy of the new space is 2 to the some polynomial, which captures the geometry of X, polynomial of n plus the entropy of X precomposed with some linear transformation of n. So here's some unknown constant factor, and here's some polynomial. But apart from that, which depends on the geometry of X, the geometry of the new function space depends basically on exponentially on the entropy of the original space. And this means, of course, we can climb up and we can apply that to X equal one of these spaces or X equal one of these spaces. In particular, all spaces of functions from here to compact to Cantor space have exponential entropy, and if we keep iterating that, then when we get higher order function space with doubly exponential entropy and so on, climbing up step by step hierarchy of types, and similarly climbing up a hierarchy of towers of exponentials in the entropy. Okay, so these are the notion of entropy and examples of spaces with various entropy. And now we can finally construct our standard representation to prove the remaining point A of the polynomial main theorem, namely that every compact metric space with at least entropy n to the epsilon for some epsilon, arbitrary positive epsilon. So what is not covered is, for instance, logarithmic entropy. This is not covered by the hypothesis, but then again, logarithmic entropy is a very strange spaces, to be honest, very disconnected. So here's the construction of a standard representation, which in particular proves that there exists one. Namely, let's fix a natural number n, and we know by the definition of entropy that there are 2 to the eta of n balls of radius 2 to the minus n, which cover the space X. And let's take the centers of these balls. Let's denote them Cn, where n now ranges from 0 up to 2 to the eta of n minus 1. Order these centers or these balls in some way, finitely many, 2 to the eta of n balls, and do that for every n. Now the representation is defined as follows. A name of a point x in this space with respect to the standard representation is a list of natural numbers, namely a list of indices of which ball of precision n of radius 2 to the minus n, actually 2 to the minus n minus 1, contains x. Such a ball must exist because these balls cover the space, and we deliberately make the balls a little bit smaller. So we need to kind of move up to higher precision balls, 2 to the eta of n plus 1, and take the index. Maybe there are several extra balls that contain x, that is possible. We just take any one and take its number according to our fixed numbering. And then that's going to be part of the name. And so we concatenate all these indices for the next higher precision n plus 2, n plus 3, and so on. We get a different index, maybe a different ball with smaller radius contains x. And all these indices we concatenate in binary. And the n index basically has length, binary length, eta of n plus 1, because well, the value is at most 2 to the eta, and therefore the binary length is at most eta, right? And the plus 1 comes here. So that a name is actually a concatenation of all these binary strings of length eta of n plus 1, so that if we fix the first n binary strings, that means we fix also balls that contain x, and therefore if we change all subsequent indices in the name, that will affect the point x that is represented by this name by no more than 2 to the minus n plus 1. And that means that the modulus of this representation is given by the first binary strings for the first n plus 1 binary string, and each one has this binary length, so that the total binary length of these first n strings is this sum. And so let's bound this sum. This sum is obviously bounded by, well, entropy is non-decreasing, so we can bound this by the largest term in this sum and multiplied with a number of terms, which is this number. And now comes the hypothesis that the entropy is growing at least with this. So we can bound this actually with entropy raised to the 1 over this, right? And in total, together with this, we get an upper bound in terms of polynomial of the entropy of 1 plus 1 over epsilon. Okay, and this is exactly polynomial, right? So we have a polynomial slack here, actually much less. We have just a constant shift, and we have a polynomial slack here, namely raised to a constant power. And this is a this representation satisfies the first condition, and I won't go into the proof that it also satisfies the second condition, namely the optimal reducibility condition. And this is the last slide of today's lecture, namely, as you recall, function spaces have exponential entropy, tend to have exponential, at least exponential. And this is of course a problem when we want to represent them, because according to Florian's lemma, any representation, its modulus, when post-composed with the entropy of the domain, which here is the Cantor space, has linear entropy, is an upper bound to the entropy of the space it is represented. So we want to represent a function space where the left-hand side here is exponential. Then it means that also the modulus of the representation must be exponential, and that's bad. Okay? And why is the entropy of function spaces exponential, generally speaking? Because we can encode, so these are kind of one Lipschitz function. These heads are carefully scaled to so that these slopes are at most 1, and it's 1 Lipschitz, right? But in this way, we can encode exponentially many different binary strings into this function space, right? So these are exponentially many functions. And this is the reason why function spaces tend to have exponential entropy. So how can we represent them? How can we have representation that can break or void the Steinberg lower bound and have exponential modulus only? One way of looking at this problem is by looking at the domain, basically the domain of the representation being Cantor space. That's the bottleneck, right? Cantor space having linear entropy. So here we have a modulus composed with the entropy, which is linear. And if we can replace it with some other space that has larger entropy, then there's a chance to have modulus of continuity, which is maybe only polynomial. And to arrive and find this larger space, let's consider Cantor space as the space, well, it's a space of infinite binary sequences, but we can also identify the index natural number with the set of all unary finite strings, right? So representing any natural number in unary, then that's the same space. And this is a good way of looking at things because it amounts to having sequential access. Sequential access in the sense that in order to access such an element, we need to, yeah, as you recall the while plus program, we need to apply the shift command m times in order to access the mth element in that sequence, right? Recall while plus. And that is kind of reflected by this unary encoding. So binary length of the unary encoding is coincides with its value. And that is a problem that makes the application functional, not polynomial time computable, even already on Cantor space. So recall that this is a set of non-expansive functions from Cantor space to Cantor space. Here's our notation. And given such a function from Cantor space to Cantor space, let's call it x prime by borrowing terminology from functional analysis with a dual space. Only here we're not restricted to linear, but instead we're restricted to 1 Lipschitz. And given an argument to that function, another element from Cantor space x, plug that in to arrive at an element of Cantor space. This is our application mapping. Given a function and an argument, apply the function to the argument and return the value. And this is not computable in polynomial time. Well, because this space has so large entropy, there's no way to present that to any computation. Computation must apply a shift command, must skip exponentially many bits to arrive at the information of the function we're interested in. But if we instead proceed to this basic space, where the ground space is a set of all 1 Lipschitz functions from C to C, right? This here, then application becomes polynomial time computable. So let's have a look at this space here. Why is this equal? This is a function space, and this is a finite discrete space. But this picture explains this equality here, namely, recall that a 1 Lipschitz function from Cantor space to Cantor space means that the first n entries of the value of such a function are determined by the first n entries of the argument. So any path here is an element of Cantor space, and a finite initial segment of length n, like from here to here to here, that is already what determines the first n entries of the value. So consider here the edges as indicating the bits of the argument, and the nodes being labeled with the bits of the value. Then we get a one-in-one correspondence between these two set and this two set, right? So this is basically this set function from finite binary strings. Here's a finite binary string to the label of the node that is indicated by this finite binary string. That's the right-hand side. And these two, yeah, can be identified. And so the right-hand side here, this is something that an Oracle machine can naturally compute, namely by making an Oracle query finite binary string, let's say polynomial or linear length, and return yes or no answer from the Oracle. So random or indirect access, replacing sequential access with random or indirect access naturally amounts to proceeding from Cantor spaces, big space for representations, to this space as domain for representation. And this space has exponential entropy, as you see here, and therefore representation that built on top of this space have a chance to have a polynomial modulus of continuity when representing other function spaces. Okay, and this amounts to having logarithmic cost for accessing the nth element, namely logarithm amounting to the binary length of the argument string here. Okay, so that's why in the sequel of this lecture, we're going to consider also this as a basic space for representations. And for now, let's recall what we've discussed. We discussed computational complexity of single elements of points in metric spaces. We've discussed computational complexity of functions between metric spaces. We've asked about quantitative correspondence between computability and qualitative computability and qualitative continuity. And we saw to get such a correspondence, we need to have a quantitative strengthening of qualitative admissibility, and we've devised one such notion very carefully, namely two conditions. First, the representation must have a modulus of continuity, which is not just polynomial, but polynomial in the entropy of the space it is representing. And second, it must have an optimal reduction. Any other function must admit a polynomial reduction to this representation. And in this case, we could prove the three claims of the polynomial main theorem. First, every compact metric space with at least entropy at least bounded from below by some power law has a polynomially admissible standard representation. And second, there's a quantitative correspondence up to polynomial slack between modulus of continuity of function and between realizers of that function. And then we recalled what entropy actually is. It's a quantitative notion, a version of qualitative compactness. And we proved that indeed the spaces, compact metric spaces with sufficiently large entropy, which include basically all reasonable examples, admits a standard even representation, polynomially standard representation. And if we want to represent spaces with exponential entropy, such as function spaces, then we should replace Cantor space, which has linear entropy, with some space of exponential entropy. And for example, the space of one-Lipschitz function from Cantor to Cantor space, which is basically the same as a set of all complete labeled binary trees, 0-1 labeled binary trees, is such a great space. And yeah, that's all for today. Thanks for your attention. And next time we're going to talk more about coding, quantitative coding theory for compact metric spaces, and notions of quantitative continuity for multifunction. Goodbye.